All right, my friends, we're going to take a little look at related rates for those of you who are beginning your study of calculus. We'll start with a simpler problem and then we'll ramp this up and look at something a little tougher. So first we'll start with if the radius of a circle is growing at 2 centimeters per second, which is a constant rate of growth, let's find the rate at which the area is growing when the circle has, well, first a radius of 1 centimeter and then a radius of 3 centimeters. Now, why you might get different answers for, say, part A and part B, that's evident if you draw a little picture of what's happening. So imagine the circle that starts real small and then starts to grow in radius at a constant rate. Well, when the circle is, say, 1 centimeter in radius, and we let a little wiggle in time go by and we add some radius to it, you would add this sort of magenta-colored ring of, say, additional material. When the circle has a radius of 3 centimeters, when you add that same little bit of radius, say over a given amount of time, you would add this bluish area. And you can see that the bluish area is larger than the magenta area. And so what happens is as the radius of the circle grows, the rate of change of the area is going to get larger and larger. So let's see that play out. Well, so if we want to relate the rate of growth of the area to the rate of growth of the radius, we first just need to write down how the area and radius are related. Well, of course, they're related as A equals pi r squared. So this relates the area and the radius. Well, now we would need to relate the rate of change of the area to the rate of change of the radius. Well, this is where the chain rule comes in. If we want the rate of change of the area, we have to take the derivative of this expression with respect to r and then multiply by the time rate of change of the radius. So this is just nothing other than the chain rule. Well, so let's go for it. We'll use the chain rule on this expression. So we have dA dt equals, well, we have to take the derivative of this expression with respect to r. So you bring the exponent down in front and then reduce it by 1. So you'd get 2 pi r to the first. So that's here. And then you just multiply by the rate of change of the radius, which is actually given in the problem to be 2 centimeters per second. And so we now have an expression that relates the rate of change of the area to the rate of change of the radius. And so we can just start plugging in some numbers now. So let's do part A. So dA dt is going to be 2 pi times the radius of 1 centimeter for part A, and then times dr dt, which is just going to be 2 throughout this whole problem. And you can see when you multiply all this together, you'll get 4 pi centimeters squared per second of additional area. Right, that's the rate at which we're accumulating area when the circle only has a radius of 1 centimeter. Well, to do part B, we just need to plug in some different numbers now. So dA dt, again, is just 2 pi r, where now the r is equal to 3, times the rate of change of the radius, which is still 2 centimeters per second. And you notice when you multiply all this together, 2 times 3 would be 6, times 2 is 12. So now it's 12 pi centimeters squared per second. So we're actually accumulating area now at 3 times the rate that we were before, which actually makes sense because if you look at the rate of change of area, it does just go like the radius. It's proportional to the radius. And so if we're out at 3 times the radius, we'll have 3 times greater rate of change of area. And so that's a pretty standard related rate problem. You'll see something like that pretty often. We'll look at a slightly more difficult case of a related rate problem, pretty popular one. And this says if water is being added to a 60-degree cone-shaped cup at a rate of 5 centimeter cubed per second, find the rate at which the water level is rising when the water depth is, well, these two values. By a 60-degree cone, I mean that's the angle at the base of the cone. So let's draw a little picture of this so we can figure out what's happening. So the idea is you have this cone. The bottom angle here is 60 degrees. And you just start filling this thing with water. So it starts with no water in it, and then the water is just going to go up and up and up and up. What we're doing, though, is we're adding a constant volume of a water at a constant rate at a constant rate such that the volume that you're adding is per second, let's say, is constant. Well, the thing is, when you are down here in the lower section of the cone, a given volume, added volume of water is going to make the level rise quite a bit. Whereas you get higher and higher, as you add that same volume, the level's not going to rise quite so much, just because this cross-sectional area is growing and growing and growing as you go up. And so we're supposed to find the rate at which the water level rises. Well, from the picture, you can anticipate that you're going to get a much faster water level rise when you're near the bottom than you will when you get a little higher. So let's go for it. Again, we're trying to relate the rate of the volume per time to the rate at which the height increases here. So dV dt and dH dt, we're trying to relate. Well, first then what we need to do is relate the volume and the height that we are. Well, we know that in general for a cone, the volume of a cone is 1/3 pi r squared times the height of the cone. But where this expression's not quite good enough for us yet is we really just need a direct relationship between v and h, but unfortunately we have this kind of confounding variable r in here. Well, so what we need is just an expression where v is purely a function of h, not with a changing r in there also. Well, so we can do that because we know the angle at the bottom of this cone. So as it turns out, this radius is just h tangent of 30. Now, why 30, even though this is a 60-degree cone base? If you look at the relationship between r here and h here, you can see that the relevant angle, if you have a little right triangle here, the angle that we need to worry about is actually half of the cone. So if you imagine running a vertical line from the base of the cone right here to the end of this arrow that represents the radius, we have this little triangle that's here. And the angle sort of from the apex of the cone here, from the vertical to the edge of the cone, that would be 30 degrees if this whole thing is 60. So this radius is just going to be h tan 30. Well, so then we just need to substitute that in there. Well, so tangent 30, as it turns out, is root 3 over 3 or 1 over root 3. And then we just need to square that h root 3 over 3 and just shove it in for r squared. And so when the smoke clears, you get this expression for the volume of the cone purely in terms of how high the water level is. So it would be, well, 1/3 pi. You get an h cubed because you have this r squared would kind of give you an h squared, but then you have another h floating around here. And then root 3 over 3, if you square it, it'd be 3/9, otherwise known as 1/3. So there's our volume of a cone purely in terms of the height, if it's a 60-degree base angle. And if you simplify that a bit, you'll just get pi h cubed over 9. So that relates the volume and the height. Well, we're supposed to relate the rate of change of volume to the rate of change of height. Well, so we can go for it. And again, it's going to be chain rule. We want the rate of change of volume. By chain rule, that is going to be dV dH times dH dt. So together, that product will give you dV dt. Well, so let's apply that to this expression. So dV dt is going to be, well, we need to take the derivative of this expression with respect to h first. So you bring the 3 down, the exponent down in front, reduce it by 1. So you get like 3 pi h squared over 9, otherwise known as pi h squared over 3, and then times dH dt. Well, so we have this expression relating the rate of change of volume to the rate of change of the height. Well, we're given the rate of change of the volume. It's 5 centimeters cubed per second. So we're just going to put a 5 in for dV dt. And then the only unknown is going to be dH dt. So we've basically solved the problem. So let's do it for these two cases. Well, so in part A, we have dV dt equals 5 equals, well, pi times, well, the height is just is 1 because the water is supposed to be 1 centimeter deep at the beginning. 1 squared over 3. dH dt. And so if we solve for the HDT, I'd multiply the 3 over, you'd get 15, over pi. 15 over pi happens to be about 4.77. So that's the rate at which the level is instantaneously growing when this thing happens to be 1 centimeter high. We can do part B similarly. So again, we have dV dt equals 5, because you're just adding water at a rate of 5 centimeter cubed per second, equals pi times, now the depth is 3 centimeters, so that's our new height, 3 cubed divided by 3, and then times dH dt. So this is our only unknown, dH dt. And so it looks like we are going to get, 15 over 9 pi. And so if you work that out, you'll get about 0.53 centimeters per second for dH dt. And it makes sense that this thing would grow slower once you're at 3 centimeters high as opposed to 1 centimeter high, because each additional chunk of volume would cause a smaller change in height. So conceptually, what I'm supposed to be drawing here is this magenta volume is supposed to be about the same, or the same, as this blue volume. And so that's how you would find the rate of change of the height of a cone that's filling up with water. Hopefully you found this helpful, and thanks for checking it out.